Hey guys, and welcome back to another video on the channel. In today's video we're going to be finishing off the Math Methods Paper 1 short response from the 2021. I did these previous questions in a previous video. I'm just going to be finishing off this exam pretty much. So last video we just finished question 17 and now we're going to be moving on to question 18. So yeah, let's get straight started. So the function f of x has the form given by f of x is equal to 3 log base 2 of x plus a plus b. The function g of x has the form given by g of x is negative log base 3 of x plus c plus 5. The sections of the graph of the two functions are shown. Determine the values of a, b, and c. Okay, so we can't really do a lot of stuff with this at the moment, mainly because our log laws don't work because these things have two different bases. So you wouldn't be able to equate them to each other and solve it very easily. However, we can see from the graph they do intersect at a point here. Now we can actually work out this point because we've got this scale here. We know that's 5, that must be 4, 3, 2. And this here must be 1, 2, 3, 4. So we know that coordinate there they have in common. So what that pretty much means is when x is equal to 2, y is equal to 4. They both share this point, both functions. So this means 4 is equal to 3 log of 2 of x2 plus a plus b, and 4 is also equal to negative log base 3 of x plus c plus 5. So what I did there pretty much is I substituted x equals 2 into here. I know f of 2 will be 4, and I know g of 2 will also be 4, so I replace those with the 4's there. And then I replace the, that's not meant to be x, sorry. That's meant to be 2. So all I did was replace the x's, as seen here, with the corresponding 2's. So now I've got pretty much two equations I can solve for, alright? At the moment, I can't really solve for anything particularly at the moment. However, there's another point we're given as well. So if we take a look at f of x, that's not the only point they have in common. We also have this point down here for f of x. This is the point 0, 1. So that means when x is equal to 0, y is equal to 1 for f of x, not g of x. Okay? So that means if I substitute in, if I have f of 0, that's going to be 1. So in other words, I have 1 is equal to 3 log base 2 of, and then I replace the x with 0, so 0 plus a plus b. Now, we've got three equations we can use. So what we're going to do straight up is pretty much rearrange this to get b as the subject. So if I rearrange this, I'm going to have 1 minus 3 log base 2 of a is equal to b. Now I can substitute it, this guy, into this equation here because b appears there. And then we've got logs with the same bases and only one variable to solve for. So if I did that, this is what I'm going to get. Let's rub some, actually we've got a bit of room down here. So we have 4 is equal to 3 log of 2 of 2 plus a plus b, but b is this thing here, so it's going to be plus 1 minus 3 log of 2 of a. Now we just got to solve for a pretty much. And then once we find that, we can substitute that back in here and then we'll have b, and then we can eventually work out c, because as you can see, this c is actually probably the one you would find first. I've just decided to go the longer way and get the other two out the way first. Like, you can just rearrange it and find c straight away. But let's just do this first. So what I'm going to do is pretty much before I apply the logs, I'm going to move these powers up there pretty much, okay? So I'll have 4, and then I'm going to move this 1 as well overwards. So 4 minus 1 is equal to log base 2 of 2 plus a all cubed minus log base 2 of a cubed pretty much, okay? What I can do now is this is going to be 3 is equal to log base 2 of divide by, so we'll have 2 plus a all cubed, all on a cubed, And then all I've got to do is rearrange this. So I have 2 cubed is equal to 2 plus a all cubed on a cubed. And what I can do now is actually take the cube root of everything, pretty much. And it'll cancel that, that, and that, pretty much. So we'll have 2 is equal to 2 plus a on a. So what we're going to have is pretty much 2a is equal to 2 plus a. So therefore, my a is going to be equal to 2, because I'm minus a here, a equals 2. And that's what I do for a straight away. So I'll write up here, a equals 2. And now I'm going to do is pretty much substitute that, what I've found here, into here. So the reason why that's good is because, well, for start off, if I sub that into here, I have 1 minus 3 log 2 of 2 is equal to b. Now, if you have log base a of a, that's just 1. So in this scenario, this turns into 1. So we have 1 minus 3 is equal to b. I'll make that capital so it makes a bit more sense. That means b is equal to negative 2. And that's my answer for b. So b equals negative 2. Right, I'm going to rub the rest of this stuff out because I don't need it anymore. And I'm going to try and find c now using this equation I've circled pretty much. So, once I rub this out, let's solve this for pretty much c. So I'm going to move the 5 over, so I have 4 minus 5 is equal to negative log of base 3 of 2 plus c. This is going to turn to negative 1, but we also have a negative over here, so we can cancel that by dividing by negative 1. So we'll have 1 is equal to log base 3. I can rearrange that into an exponent by going 3 to the power of 1 is equal to 2 plus c, minus 2, c is equal to 1. C equals 1, and that's me, A, B, and C, all found. Okay. If you have any questions about this particular question, leave some in the comments, or try and rewind back and see if you can understand like clips of it. If not, yeah, I'll try my best to answer it in the comments below. But anyway, let's move on to the next question. So, question 19. A horizontal point of inflection is an inflection point that is also a stationary point. So, that pretty much means something like this. Oh, that's a terrible drawing. Let's try and draw it a bit better. So it's pretty much exactly how they've described it. A point here is a point of inflection. That means the second derivative is 0 there, and so is the first derivative. So it's a bit of a weird one, but I like how they've explained it before they've asked you to find it. So determine the values of k for which the graph f of x has only one horizontal point of inflection. Okay, so you're going to need your differentiation skills for this one. So all we're going to do is just start differentiating this. So we have f of x is equal to natural log of x on k minus k on x plus 1. Okay, so if we differentiate, k is treated as a constant, so you just have to differentiate the log. So if you differentiate a log, ln of x, that turns into 1 over x. So what we have here for that first bit will be 1 on kx. Now, I'm going to write this here because I'm going to differentiate straight away because you need to use the quotient rule. Because as you can see, you've got a function divided by another function. So we go straight to our formula sheet and look for the quotient rule. Unless you remember it very well, go straight to the formula sheet because this is the one where the order of where you place it actually matters. So go straight to your formula sheet and don't even bother, because you get given this in the exam and it's much easier just to write down off the sheet than trying to remember and then you get it wrong pretty much. So all I'm going to do is write, if you want to differentiate a function, so u on v, that's going to be equal to, and I can never remember it, so it's v du dx minus u dv dx all on v squared. So in this case here, my u is my top function here, which is negative k. So I'll go u equals negative kx, and then my bottom function is x plus 1, so v is x plus 1. So that means that now du dx just means u dash pretty much. So u dash here, if I differentiate this, that's just going to be negative k. And v dash here is just going to be 1. Okay? So all we're going to do is now plug into the formula pretty much. So that means the differential of this. Now, you'll probably need to do this in the exam, but I wouldn't write it here. I would write it on a piece of paper pretty much, on a spare bit of paper, all this working here. Because you're going to need a bit more, well, we only get a little bit of space here unless you want to write at the back of the book, because it's much easier to write all this out than to just try and do that in your head, okay? So what we're going to have is v, which is x plus 1, u dash negative k, that's being multiplied, minus u, which is negative kx, multiplied by v dash, which is 1, all on v squared, so x plus 1 all squared. Okay, so let's sort out the top. So what we're going to have is negative kx minus k. So all I did was distribute this guy in here. That's how I got that. Now I'm going to distribute this, so I'll have plus kx, because 1 times negative kx is negative kx, times by negative 1 is still going to be kx, because the negative will cancel. So we'll have x plus 1 all squared, and we can see straight away that cancels with that, so we have negative k on x plus 1 all squared. Righto, I'm going to rub a lot of this stuff out because I need a lot more working still, okay? So I can replace this bit here with the working we got here. So it was negative k on x plus 1 all squared. And then I can rub all this stuff out, okay? So what we want to do now is, because we're searching for k values where you have one horizontal point of inflection. So what that means is the first derivative needs to be 0 and the second derivative needs to be 0. So what we're going to do straight up is just find the second derivative, get all the differentiation out the way, and then deal with the algebra, because the differentiation is the hardest part, because if you don't differentiate it correctly, you're not going to get anything else correct. So it's just important to get all the differentials out of the way pretty much. So taking the second derivative is actually going to be a lot easier, honestly. We're just going to rewrite how this looks though. So f double dash of x, oh, not double dash, I'm just going to rewrite as f of x, because then we can just use chain rule. So I'll rewrite this first bit. It will be 1 on k, x to the negative 1, plus negative k, x plus 1 to the negative 2, okay? So if I differentiate this here, I bring that power down the front, so I have negative 1 on k, minus the power up here. Same here, so I'll have plus, and they'll cancel, so it'll be 2k, x plus 1, minus 3, multiply by the differential of this, which is just 1, so I can just leave it like that. And that's it, that's the second derivative, okay? So f double dash of x is negative 1 on k x squared plus 2 on k on x plus 1 all cubed, okay? So what we're looking for is pretty much when this is equal to 0. We can say when this is equal to 0, or we can solve for this one. Now, because this has a cubic term, it's going to be a bit harder to solve for x here, because you're going to get a polynomial with a degree of 3. So that means like a cubic. So all we need is pretty much, alright, for that to be true, f dash of x needs to be 0, and so does f double dash of x. So you can pretty much choose, that's a rubber, I thought it was a highlighter. You can choose this one to solve for x, or this one, okay? So I'm going to choose the first derivative, because algebraically I can see it's going to be easier, because down here this is a squared term, so the worst I can get is a quadratic, but here I can expect a cubic, and then you might need to do long division and stuff like that, which we're just not up for pretty much, because we want to save time during the exam pretty much, because you only get 90 minutes to do this. Okay, so let's just pretty much go, alright, f dash of x is equal to 0, so what we're going to have is 0 is equal to 1 on kx minus k on x plus 1. Oh, I rubbed that out. That's squared. all squared. Okay? So, what I can do, if I wanted to, is actually multiply by k on x on both sides, because that's still going to be 0, but that will cancel and turn to 1, and this will turn into minus k squared x on x plus 1 all squared, still equals to 0. So I'll rewrite it down here in a bit neater fashion. So I've got pretty much just a constant there. So all I did was multiply with kx, and that cancelled that, and then I multiplied by this on there, and that gave me that top term there. Okay. Now I'm going to move this whole thing to the other side to make it positive. So I have k squared x on x plus 1 all squared is equal to 1. Then I'm going to multiply both sides by x plus 1 all squared. So that can cancel there. So I have k squared x is equal to x plus 1 all squared. And now I'm going to expand this because I want it in quadratic form. So I'll get x plus 1 times by x plus 1. So this multiplied by this, and this, and this, and this. X times x is x squared, x times 1 is x, and then 1 times x is x, and 1 times 1 is 1. So I'm going to get x squared plus 2x plus 1. Okay? So I'm going to move this guy over to here now. So I have 0 is equal to x squared. Now notice this is a like term with that. So we can factor out an x and have pretty much plus 2 minus x, k squared on x plus 1. Okay? So all I did was move the k squared x onto the other side. And that gave me that expression there. Okay. So we pretty much are looking for real solutions. So in order for them to be real solutions, that means there's no complex solutions, no powers, no i's, no nothing like that. So since this is a quadratic term, that means if they're real solutions, the discriminant is going to be positive or greater than 0. So the discriminant is equal to b squared minus 4ac when a quadratic takes on this form here. Okay? So as we can see, that would be your a term, 1. This would be your b term, and this would be your c term. Okay? So we're looking for real solutions, and we don't want things equaling 0. So we're pretty much going to put in an inequality. The discriminant must be, and now I've got to think of it the right way, must be greater than 0. So that means 0 must be less than b squared minus 4ac. Okay? So that means 0 is less than, well, we're looking for any real solution. So your discriminant can be equal to 0, but it have one solution. So it would be a less than equal sign. Less than equal, and the b is this term. So it will be 2 minus k squared all squared minus 4 times by a, which is 1, times by c, which is 1. Okay? And now we're going to pretty much solve for k. And we've run out of room. So I'm going to rub some stuff out up here and start moving some stuff around. Move that and that. So what we have is, what was it? 0 is less than or equal to 2 minus k squared all squared minus 4. So we're just going to solve this for k pretty much. So move the 4 to the other side, and you don't need to flip the inequality because you're not dividing by a negative number. You only flip it when you divide by a negative number, not when you move stuff across. And what we're going to do is square root both sides. So we'll have plus or minus 2 is less than or equal to 2 minus k squared. So this gives us two solutions. It gives me negative 2 is less than or equal to 2 minus k squared, or it gives me this solution, 2 is less than or equal to 2 minus k squared. In this solution here, we're going to have 0 is less than or equal to negative k squared, which we can't have because that implies k is equal to 0. And if you look at our function here, if k is equal to 0, that's 0, and so is that 0. So, well, you have a divide by 0 there, and then this term would be 0. So there'd actually be no function. So that is not possible. So we rub that out and discard that solution pretty much, okay? So, minus 2, so we have negative 4 is less than or equal to negative k squared. Now we divide by pretty much the negative. So we're going to have k squared. Oh, sorry. If you divide by negative 2 squared, divide by negative k is equal to 4. Yep. And then you take the square root of both sides. So plus or minus square root of 4, which is plus or minus 2. So k is equal to plus or minus of 2. Now, you're probably thinking, where did the inequality sign come? Where did the inequality side go? Well, they specified the values of k for which the graph has only one horizontal point of inflection. So the reason why the inequality sign is gone is because our solutions is both a positive and a negative number. So it's like eventually cancels out. So all you have is pretty much an equal sign. So all you're going to have is k is plus or minus 2. So pretty much either one of these should be a horizontal point of inflection. And we can double check that, because if we substitute either one into the second derivative and the first derivative, it should be equal to 0. So let's just double check that. So if we rub this out, and we rub, we'll leave that one, get rid of this one, and if we rub this out, get rid of this, k is plus or minus 2. So f dash of just positive 2 will be 1 on 2x. Oh, that's sorry, that's not. That's still x minus 2 on x plus 1 all squared. I nearly substitute x for k, but I'm only replacing k's pretty much. So wherever the k is where one of these will go. Okay. Now we need to know when these are, where the horizontal point of inflection is. So if we actually go back to our quadratic, we can actually work that out, because we can substitute in k is equal to plus or minus 2. Now, it doesn't matter in this equation here whether it's positive or negative, because it's getting squared. So this here will tell us the x values for the horizontal point of inflection, but k is plus or minus 2. But here you can see the k gets squared, so it doesn't matter where plus or minus goes in, it's still going to end up being 4. So what you're going to have is x squared is equal to 2 minus 4. So that's going to be minus 2x plus 1. Actually, that's going to be, yeah, that'll be that. And then once you have that, you'll be able to solve that pretty much. So if you think of two numbers that multiply to give 1 and add to give negative 2, you're going to think of x minus 1 and x minus 1. So that means the only solution to this is x is equal to 1. So that means there's a horizontal point of inflection at x equals 1. So if I have this k value in all these equations, whether it's positive or negative, it'll be, oh, that's 2k, so that'll be 4, and that'll be 2. So that means f dash of 1 should be 0, and so should f double dash of 1 should be 0. Okay? So, what we can do is just sub that in. So f dash of 1 is going to be 1 on 2 on 1, minus 2 on 1 plus 1 all squared. So what we're going to have is a half minus 2 on 4, which is a half, so you get 0. And then we're going to have double dash as well. Double dash of 1 is going to be negative 1 on 2 on 1 squared plus 4 on 1 plus 1 cubed. So what we have is negative a half plus 2 cubed is an eighth, so 4 on 8, which is a half, and that is also equal to 0. So these are your k values, and the horizontal point of inflection is when x is equal to 1. Okay, but all they've asked for is k in this case here, but that's just showing that these k values work pretty much. Okay. Yeah, that's all for this question here. If you have any questions about 19, leave something in the comments and I'll try my best to answer it. Okay, let's move on to the next question now. So, question 20 is, I believe, yeah, the last question in this paper. So, question 20. At the end of the first stage of its growth cycle, the species of a tree has a height of 5 meters and a trunk of radius of 15 centimeters. In the second stage of its growth cycle, the tree stays at this height for the next 10 years. However, the growth rate of the trunk in radius in centimeters per year varies over the 10 years and is given by the function r of t is equal to 1.5 plus sine of pi t on 5. Assume the density mass per unit volume of the tree trunk is approximately 1, I'm assuming that's gram on centimeters cubed, and the tree trunk is the shape of a cylinder. Determine the ratio of the trunk's mass at the end of the second stage to its mass at the end of the first stage. So, pretty much what we want is pretty much how much is this trunk going to grow. Now, we're assuming it's growing, not getting smaller because it's growth cycle. Trees' radiuses don't really get smaller over time, they most likely get bigger. So, what we're looking at is some keywords here. So a keyword that I notice straight away is here. Assume the shape of a cylinder. And here, a lot of people won't notice this. Centimeters per year describes this function. So that means the radius at a point in time, the derivative of that with respect to time, is this function here. So this function, if you put in a t, it doesn't give you the radius at that time. It gives you the rate of change of that radius at that time because it's centimeters per year. That is a rate of change. It is not a function of giving you a particular radius. So if you want the radius at a particular time, you need to integrate the given function with respect to time. Now that is the hardest part of this question, working out that you need to integrate that, because you have to look for the specific wording. They're comparing one variable to another. In this case here, they're comparing centimeters to years. So if they're comparing two things, that is a rate of change. So if you want to give a function for that, you need to integrate it. Otherwise, we've just been given a derivative. We've been given d capital R on t is r of t, where capital R is the radius of the tree trunk at a point in time. Okay? So, first thing we're going to do before we do anything else is just integrate that function, and you'll get some marks. So, we will integrate that, and we'll label it capital R. So we'll go capital R of t, where R is the radius at a point in time. I'll just call it like that, because it is a function of time. What do they give it in? Years. Okay, years. For years. Is equal to the integral. Now 1.5 is 3 on 2. I'm just going to change that. Plus sine of pi t on 5 dt. So let's integrate this. So integrating the constant, just chuck a variable next to it. So 3 on 2 t. Now integrating here, you need to divide by the differential. So the differential of the inside function will just be pi on 5. If you divide by that, you should have plus 5 on pi multiplied by, if you integrate sine, that turns into negative cos. So you're going to have, in the end, minus 5 pi cos of pi t on 5. And then don't forget your constant c. Okay. So what is our constant c? Our constant c is our initial radius. So did we get told that at the start? At the end of the first, that's high there. Okay, so this function models the second stage of the growth cycle. So before the second stage, its initial radius we're told is 15 centimeters. So that means when t equals 0, capital R, or R of 0, is 15 centimeters. Okay. Now we're going to be consistent with our units now. So notice up here they also had this in 5 meters. If you convert that to centimeters, that'll be 500 centimeters, and we might need that later. So we're going to go R of 0 is equal to 3 on 2 times by 0 minus 5 on pi cos of 0, because 0 times pi on 5 is 0 plus c. Now that's 0, that's 15. Cos of 0 is 1, so this is going to be minus 5 on pi plus c. So therefore your c is going to be 15 plus 5 on pi. The hard part would have been noticing that cos of 0 is 1. A lot of students will put that as 0. So you need to make sure you're up to date fully on your trigonometry as well. So that means our function, I'm just going to write here, r of t is equal to 3 on 2t minus 5 pi, I can't remember what else, cos of pi t on 5 plus c, which is 15 plus 5 on pi. Okay, so if you do all that, you'll get a couple marks. I imagine you get like 3 or maybe 2 marks just from doing all this. Okay, so let's continue reading the question, because there's still a lot more in it and we need to work that out a bit more. So hurry up. Rub out. So assuming the density, mass per unit volume of the tree trunk is 1 gram per centimeters cubed, the tree trunk is in the shape of a cylinder. So go straight to your formula sheet and write down the volume for a cylinder, which is here. So volume is equal to pi r squared on height. Now we're told the height remains the same over the 10-year period, so the height is 500 centimeters. So volume is pi 500, and r changes. R isn't this function, it's this function here. So just put in, like, you don't need to write the whole function, just put r, capital R of t, all squared. Okay. So density is mass on volume. So we want to work out the ratio of the trunk's mass at the end of the second stage to its mass at the end of the third stage. So since its radius is increasing, we're imagining our tree's mass is increasing, but we want to work out by how much, hence the word ratio. But we're told, assume that is approximately this, so that means our density is 1. So that pretty much means, since our density is always going to be constant, the mass at the first stage, so I'll indicate that as m1, divided by the volume of the first stage, is going to be equal to the mass of the tree on the second stage divided by the mass of the tree in the second stage. Okay? So this is because we're assuming the density is going to be constant and it's not going to be changing. So the density is the amount of how much material is packed into a certain volume, hence mass on volume. So setting this up was the second hardest part. Now we want to know the ratio of m2 on m1. So we just got to multiply both sides by v2 and divide both sides by m1. So if I do that, that cancels, that cancels, that cancels, that cancels. So that means v2 on v1 is equal to m2 on m1. So if we can work out the volume at the end of the second stage and divide by the volume at the end of the first stage, that'll give us this ratio here because they're both equivalent. So just write that in the corner somewhere because I'm going to rub it out. M2 on M1. Right. So rubbing this out, what we're going to do is the second part of this question. So we need the volume at the end of the first stage. So that means we want the volume when t equals 0. So we work out r of 0 pretty much, because the volume of the first stage, so volume of the first stage will be pi 500 times by r of 0 all squared. So r of 0 is going to be 3 on 2 times 0 minus 5 pi cos of 0 plus 15 plus 5 on pi. And we can see that goes to 0. Now we don't know what this number is, that's what we're working out. R of 0 is equal to, now this here is going to be 1, so you have minus 5 pi plus 15 plus 5 on pi. That cancels, so r of 0 is 15. So you're going to have V1 is equal to pi 500 times by 15 squared. Now, that's going to be hard to actually work out, but you can do it, I think. So all we got to do is go 15 times 15, because remember this is a non-calc paper. 5 times 5 is 25. 5 times 1 is 5, plus 2 is 7, sorry, and then 1 times 5 is 5, and then 1 times 1 is 1. So you should get 5, 3, so that's going to be, 2 plus 1, 2. 225 should be 15 times 15. Hopefully. I will double check that just in case. Yeah, it is. Alright, I might have used a calculator, but I make the video, so I don't care. So you can do it without a calculator, as I just saw there. So that'll be 225 times 500 times pi. So what you want to do is go 500 times 225, and you can do that without a calculator as well, using one of these multiplication table. 5 times 0 is 0, 5 times 0 is 0, 5 times 5 is 25. Then we go 2 times 0 is 0, 2 times 0 is 0, 2 times 5 is 10, 2 times 0 is 0, 2 times 0 is 0, and then 2 times is 10. So what we're going to get here is 0, 0, 5, 2, 1, 1. So what we should have is volume 1 is 112,500 pi. And that's going to be important later. Okay? So, alright. What are we looking for now? We're looking for volume 2. So volume 2 is the end of the 10-year period. So volume 2, oh my gosh, I'm going to rub this out. Volume 2 will be pi times 500 times r of 10 all squared. Okay, so we're going to work out r of 10, so go r 10 and substitute wherever there's a t, pretty much replace that with a 10. Okay, yeah, that's about it. So we'll go is equal to 3 on 2 times by 10 minus 5 pi cos on 10 pi on 5 plus 15 plus 5 on pi. So 3 times 10 is 30, divided by 2 is 15. This here will be 2 pi. Cos of 2 pi is going to be 1, so we'll have minus 5 pi plus 15 plus 5 on pi. You can see those cancel. So r of 10 will be 30. So rubbing this stuff out, because all we needed was that number. So we'll go V2 is equal to pi times 500 times by 30 all squared. 30 times 30 is going to be 900. So we'll have pi times 500 times 900. So 5 times 5 times 9 is going to be 45. So add in a couple zeros. So we go 45, 0, 0, 0. So there's 1, 2, 3, 4 times by pi. So volume 2 is going to be 4, 5, 0, 0, 0, 0 pi. Right. So what we're going to do is take those numbers and then divide them by each other because we're looking for that ratio. So what was our first number? So this is our first number here, and this is our second number here. Okay? So that means volume 2 on volume 1 is the same as mass 2 on mass 1. So we're going to have 4, 5, 0, 0, 0, 0 pi divided by 1, 1, 2, 5, 0, 0 pi. Now, you're probably thinking, how are we going to do that without a calculator? Well, it's going to be a whole number because it's a non-calc paper. So we're only looking for an integer. Now, I don't know if you noticed this, but this is exactly a quarter of this. Because if I multiplied 1, 2, 5, 0, 0, if I times that by 4, I'm going to get, what, 0, 0, 20, 8 plus 10, so 0 plus 1, 4 times 1, and then I'm going to get 5, and then 4 times 4 is 5. So this number here is exactly a quarter smaller than this. So this answer should be 4. So it's increased by 4 times. And that is the answer to this question, 4, simply. That is their ratio, 4. Yeah, I hope you enjoyed that video. If you have any questions about these last questions in this paper, leave something in the comments and I'll try my best to answer them, okay? But otherwise, I'll see you in the next video.